Okay, so we have another question on the board. It says a uniform cylinder, cylindrical vessel has a cross-sectional area of 120 cm square. It is filled to a depth of 150 meter with water, and oil of thickness 50 meter floats on the water. So this is the gravity, this is the density of oil, and the density of water. The atmospheric pressure is given as this. Calculate the absolute pressure at the base. So that will be the total pressure that will be given by water and the oil. So we'll calculate that, and the force acting at the base. So the first thing we'll do is to get the pressure due to column of water. Okay, so pressure due to column of water is given as height, density, pressure. Height, density, gravity, height. Density, gravity, height. Okay, so density, gravity, height. So the first thing I'll do, my density is 1000 of water, gravity is 110, then height is 150 meter. Okay, so by the time I compute it, I'll be getting 1, 2, 3, 4, 5. Okay, over 100. So I'll be getting 15000 Newton per meter. That's the pressure due to water column. The next one is pressure due to oil. Pressure due to oil. So this is again density, gravity, height. Density of oil is 700 times gravity is 10, and times the height. Now the height will now give us the total height. That is from 50 cm. This is 50 cm. Okay, 50 cm over 100. Sorry, this is in cm, not in meters. I was wondering. That is converting 150 to 100 to meter. So by the time you finish, you'll be getting the absolute the pressure due to oil as 3,500. 3,500. Okay, so this is Newton meter square. Okay, so if you add the two of them, you're going to get the total pressure, the absolute pressure at the base. So let me just put it here. Absolute pressure at the base. Absolute pressure at the base. Is equals to pressure due to water and pressure due to oil. Add them together, right? So 1,500 or 15,000 plus 3,500. So that will give me 119.8 119,800. That's Newton per meter. So that's the pressure that we're given by the two of them. Now the next question, number 2, here says force acting on the base of the cylinder. Force acting on the base of the cylinder. So for this one, we'll need to consider the area, the area, because pressure is equals to force over area, and we have gotten the pressure from the first question, and the area, cross-sectional area, will come from the fact that we have this at the cross-sectional area. Okay, so we'll just say force is equals to pressure times area, and the pressure for the previous question is 119,800 times 120. So, but this is in cm square, so I'm going to make it to meter square, that times raised to power 4. So by the time I compute this, the force will be given as 1437.6. 1437.6. That should be newtons. That's the answer for this second question. So move on to the next question. So another question here, we just have this from JAMB 2007, JAMB 2007 on still on pressure. So say reservoir is this 500 deep, fluid density inside the reservoir is 850, atmospheric pressure is 1.05 times 10 to the power 5 Pascal. Find bottom pressure. So the pressure at the bottom is actually the sum of the two pressures. Atmospheric pressure, pressure atmosphere, plus pressure due to fluid. Atmospheric pressure is already given as 1.05 times 10 to the power 5. And pressure of fluid is density, gravity, height. That's the formula. We'll just compute it inside there. Okay, density for that fluid is what? It's 850. Gravity is 10. Height is 500. Consider this as pressure due to two things. You have the reservoir like this, and this is the fluid. So this fluid has that pressure at the bottom. Also, atmospheric pressure is up. So pressure at the atmosphere plus this one will give you pressure at the bottom. That's what we are always doing like this. So by the time you compute this, you'll be getting 4.3, 55 times 10 raised to the power 6 Pascal. So this is the combined pressure of atmosphere and the fluid. So go to the next question. Okay, so this question is from JAMB 2004. JAMB 2004. It says a man exerts this Pascal, 2.8 times 10 to the power 3 Pascal on ground. Fit area is this. Find the weight. Find the weight. Force is equals to pressure is equals to force over area, right? Pressure is equals to force over area. Okay, so but now we're looking at it as weight. It's the weight we're looking for, right? And the pressure here is given at 2.8 times 10 to the power 3, and the weight is what we're looking for. Then the area of the man's feet is 4 times 10 to the power minus 2. This is square, right? 4 times 10 to the power minus 2. So to get the weight, I will just multiply 2.8 times 10 to the power 3 by 4 times 10 to the power minus 2. So weight of the man will be seen to be 112 Newton. That's the answer. Okay, so this one has to do with contact pressure. Contact pressure. So the next question. Okay, so we have another question on the board. It says that pressure is 2.0 times 10 to the power 5 Pascal at one volume. At one volume. If volume halves, that is, if this one becomes half of itself at constant temperature, what is the new pressure? So this is a classic Boyle's law problem, which states that initial pressure volume combination is equal to final pressure volume combination at constant temperature. So P1 V1 is equal to P2 V2 at constant temperature. Given initial pressure as initial pressure P1 in the question as 2.0 times 10 to the power 5, and also final volume V2 is equal to half of V1. Then we can now apply this Boyle's law, this formula, and impute what we have. Final pressure, which is P2, will be P1 V1 over V2. That is making this one such a formula. We'll get this one. So we can now impute what we have here. P2 is equals to P1 is 2.0 times 10 to the power 5 times V1. V1 is expressed, is still V1, but V2 is expressed over V1 as half V1. So this can cancel this. And this one will be P2 is equals to 2 times 10 to the power 5. All right? That will give us 4 times 10 to the power 5 Pascal, right? Yes, so it goes to show that when the volume is half at constant temperature, the pressure also doubles. It doubles from here to here. This explains this relationship. Okay, so we'll go to the next question. Okay, so I have this on the board. It says a 1 meter deep tank full of water. This is the volume, the water with this density and the gravity. What is the pressure at the bottom? So this is just simply pressure. Pressure is equals to density, gravity, height. Pressure is equals to density of water is given as 1,000. Gravity is 10, and the height is 1. So the pressure is 10,000 pascals. 10,000 pascals, or 10 raised to the power 4, or 10 raised to the power 4 Pascal, or 10 kilopascal. Anyone? Anyone? Okay, so number 7 says that liquid A density is 900 kilogram per meter cube, rises 26 cm. What is the rise for B of density? So you have two liquids in a tube. So this problem involves liquid columns in equilibrium, often seen in YouTube manometers or capillary rise comparisons. Yes, where pressures at the same level, horizontal level, must be equal. So given that liquid A, the pressure, atmospheric pressure, the pressure is 900 kilogram per meter square. Okay, and the rise for liquid A is 26 cm. We'll also convert this to meters. When we do that, I think we'll get 0.26 meters. All right. So this is density, height. Then there's a gravity, of course. For liquid B, the pressure of B is 1,000. This is likely to be water. 1,000 kg meter cube, and the rise of liquid B is what we're looking for. We don't have it. So we are going to be using the principle that at equilibrium, at balance, at equilibrium, pressure due to both columns must be equal, right? So pressure of liquid A is equal to pressure of liquid B. So this is density gravity height of A and density gravity height of B. Okay, so let's do that for A. Density is let me just put the subscript so that we know B. Okay, so density for A is 900, gravity is 10, height is 0.26 is equals to density for B is 1,000, gravity is 10, and height is unknown. Even this one can cancel this one. So I have 900 times 0.26 over 1,000 is equals to height of B. Okay, so by the time I compute this, my calculator, I'll be getting the height of B as 23.4 cm. That's the height of B. So that's the answer. Okay, so we have another question on the board. This is actually WAEC 2015 question. So it says that the barometric reading is this. I try to summarize the question. Just barometric reading is 73 cm of mercury. Calculate pressure 30 meters below water. Okay, so there's barometric pressure, as is pressure of atmosphere interfacing with the water, and the water too also exerts another pressure at the bottom. So calculate the pressure 30 cm below water. So at this 30 meter point, sorry, that is where we're going to calculate pressure. We're going to add the pressure of both water at this level and the atmospheric pressure. So we say total pressure, let's call it P total, is equals to P atmosphere plus P water, that is at 30 meter. Okay, so this is the total pressure. So we'll now look for the pressure at atmospheric pressure. We're going to do some conversion to convert barometric pressure to Pascal. So we'll just convert barometric pressure to Pascal. That's this one. So P atmosphere, P at is equals to density gravity height. I like that formula. Density gravity height. This density is this one. Yes, is density. Look at it, sorry. Density. So it is mercury, 13600, okay, times gravity is 10, of course, or let's use 9.8. We're not giving here, but I got this is the right value. Then height is 73 cm of mercury, but you know this is 73 cm, so change to 0.73 meter. By the time you compute this, I'll be getting 97194.4 Pascal. Okay, so this is for A atmosphere. So for P water, pressure of water at this distance or height. So this one will be density gravity height again. Density gravity height. Density of water is 1000. Okay, and the gravity is times 9.8 and height is 30 meters. So by the time I compute, I'll be seeing a value of 294,000 Pascal. So I'm going to be adding this value and this value to get my total. So P total will be 97194.4 plus 294,000 Pascal. So combination of the two will give me 3.91 times 10 power 5 Pascal. So that's the answer. Okay, so we have 2 more to go. Okay, so we have a question on the board. It says density bottle weighs 2 Newton empty, 5 Newton with water, 4 Newton with oil. Find the relative density of oil. So we know that relative density is equals to weight of oil over weight of equal volume of water. Weight of oil over weight of equal volume of water. Okay, so we know that the weight of empty bottle is 2 newtons. Okay, weight of empty bottle is equals to 2 newtons. Clear here? So with water, weight with water is equals to 5 newtons. Then weight with oil is equals to 4 newtons. So I'm going to be doing a series of deductions from here. So if these are the parameters that we have, weight of water weight of water will now be the difference between this and this. Difference between this with water and with empty bottle. So I have 3 units. So this is actually the weight of water. Then the weight of oil, is equals to 4 Newton minus 2 Newton again, is equals to 2 Newton. Okay, so now relative density is this oil over water, that's 2 over 3. So relative density of oil, RD of oil, is equals to weight of oil, which is 2 Newton, over weight of water, which is 3 Newton. It will give me 0.666667. It's not just the value, just a ratio, 0.67. So that is the relative density of the oil. Okay, so we have this on the board. It says the atmospheric pressure due to water is 1.6 times 10 to the power 6 Newton meter. What is the total pressure at the bottom of the ocean? 10 meter deep. Density of water is this, and gravity is this. So we have density, gravity, height. We should have 2 kinds of pressure acting. So at this point, I need to draw this. I've been saying this. Let's say this is the ocean. This is the ocean. So this is the ocean, body of water. And let's say this is 10 meter deep. Might not be at the bottom of the ocean. Okay, 10 meter deep. Okay, let's do it like this. 10 meter deep. Okay. So this is water actually. So I call this side water. And this is the distance from water top to water bottom. But there is a body of air on top like this that also is that pressure. So this body of air, there's an atmospheric pressure that is given as PA, which is 1.3 times 10 to the power 6. So this one is already computed. But we need to also compute the pressure that this water will give at the bottom. So we add this pressure due to water and pressure due to atmosphere. So total pressure, P total is equals to P atmosphere plus P water. P atmosphere is already given as 1.3 times 10 to the power 6 plus P water can be gotten by density, gravity, height, of course, 1.3 times 10 to the power 6 plus density of water is 1000, gravity of water is not water, gravity is 10, and height is 10. So by the time I compute this, I have 1.3 times 10 to the power minus 6, not minus 6, plus 1, 2, 3, 4, 5. That is 10 to the power 5 Pascal. That is 1 plus 1 times 10 to the power 5 Pascal. So if I do the addition of this, I'll be getting 1.4 times 10 to the power 6 Newton meter square. So this is the answer. So I have, with this video, I've been able to cover extensively questions, calculations on pressure, both on in fluids, pressure in fluid, yes, and you can check the description for more questions, and also the comment section, comment on what you observe. If you like this video and you're not yet subscribed to our channel, kindly subscribe to our channel. So I hope this video has been informative for you, and I'd like to thank you for viewing.